So my name is Barbara Streiffert, and I work at Jet Propulsion Laboratory. Somebody earlier this week asked me about flying airplanes, and of course we don't do any airplane work whatsoever. We actually fly spacecraft, and I have a few pictures, if I can find my cursor. We have Cassini, and that's been orbiting the Saturn system for about 10 years. On the other side, we have Curiosity, which actually landed about 2 years ago and has been roving Mars. I have two missions that are in preparation for launch. There's InSight, which is a lander for Mars, and it will be launching. The launch was just delayed, and so it's probably going to be launching early in next year. And then there's SMAP, which has the worst acronym in the world because its name really is Soil, Moisture, Active, Passive. And so that is going to be an Earth orbiter, and it's going to determine the moisture in the soil. So I have a really long agenda, and my facilitator almost had a heart attack. I'm not going to go through the agenda at all. I'm just going to get right to it. So Jet Propulsion Laboratory sends spacecraft to the solar system. We have planets, moons, asteroids, comets, and we even have some observatories. And so I've talked about some of these missions. We have 2 rovers on Mars, Opportunity and Curiosity, 2 orbiters around Mars, Odyssey and Mars Reconnaissance Orbiter. We have an orbiter around Saturn, which I told you about. We have a mission to Ceres, an asteroid, and that mission is called Dawn. We have several Earth orbiters. One of them is Jason. Jason actually determines the health of the ocean and identifies when we have El Nino or La Nina events, and those mean lots of rain for California, and we really need that. And we have several other missions that are being planned. For this presentation, I will talk most about Curiosity and use that as my example. We have various different types of testing that's performed at JPL, and I have to tell you about some of it so that maybe you can understand what kind of testing we actually do in my group. So, of course, we have our own language. And so I have to give you a few definitions. Flight software is actually the operating system on the spacecraft. There's ground software, and that's the software that's actually used on the ground, and it simulates and processes commands, and that's the software I work on. And then the other portion of ground software is to process telemetry, which is the data that comes down from the spacecraft. So uplink, everything that's going up to the spacecraft, it's pretty easy to remember. Downlink, everything that's coming down from the spacecraft. An activity is a group of commands that are sent to the spacecraft to perform a task. A sequence is a group of activities and commands that are sent to the spacecraft. And we have software classifications. Class A is human rated. These all came from NASA. We typically don't do Class A because we have robotic missions, so we don't usually deal with human rating. But we do have Class B software, and that's mission critical. That means that if this software doesn't work correctly, that you could end the mission. Class C software is mission important. That's generally things like science, data collection, the science instrument software. Almost everything now has a processor on it, so it would be the science processor. And then Class D software, and that typically involves test software. So we have, generally our applications are built in 2 halves. We have the mission independent piece called core, and then we have the mission specific piece. And I'll get to why we need to have 2 different halves. The mission specific piece has all of that particular spacecraft's commands, activities, all of the information about that specific spacecraft. The application independent piece, or core, is the group that I work with. So this is some background. We have 19 applications. They're all in maintenance. There's a combination of Class B and C software, and we have over 1,000 automated tests. The deliveries, well, I wrote this slide quite a while ago. Deliveries vary. Usually they're once or twice a year and only include the requested applications. However, when missions are approaching launch, deliveries are more frequent. Well, we have insight, and so now we're delivering like every month, every other month. So, that's what happens when you have a piece of when you have a spacecraft that's getting ready to launch. You're delivering all the time. Deliveries are, regardless of what kind of delivery it is, whether it's an engineering delivery, whether it's an exploration delivery, whether it's a formal delivery, all the testing has to be done. And if the mission has an urgent request for the software, then and they don't have a workaround for that particular problem that they're having, then we have to drop everything, we fix the problem, and re-deliver it. Typically, missions have their own testing processes that they go through, and so I'm going to go through some of those different processes. So this is just a picture of the different applications that we have, and I'm not sure if, oh, here we go. This one is a context-sensitive editor that we use for entering commands and activities. And then we have difficulty with finding my cursor. The command simulation is another piece of software that we use. We also have science and engineering planning software. We have command translation. The spacecraft typically wants the commands translated into binary, and then it wants them packaged in a certain number of bits with a certain kind of header with a checksum attached to it. And so all of this software does all of these things. All of the ones on, let's see, I guess it'll be your right, that are in blue, that's a sequence, what's called a sequence engine, and that handles the various different threads dealing with the sequences that we send up. And remember, a sequence is a group of activities, which are tasks, and commands. So this is what the problem is. Spacecraft characteristics. Each spacecraft is one of a kind. There's no other one like it, except for Mars exploration rovers. They were identical. That's Spirit and Opportunity. And each spacecraft has its own design, its own set of instruments, its own operating system, which is the flight software, and its own set of experiments and activities and its own goals. Because we're not going to just down to the corner market every day. We're going to different space solar system elements. You're not going to have the same goals for a rover or a lander or an orbiter. They're not going to have the same goals. So everything is different. So just to give you an idea of the size of what we're talking about, each spacecraft has many commands, and they can be operated basically in almost any combination unless there's a flight rule that says they can't. And for example, Curiosity has about 3,000 commands, and about 1,000 of them are used regularly. So if I tested permutations of 1,000 commands in groups of 10, that's if they're sending up that group of 10, that would be 955 octillion possibilities. And that's 10 to the 27th, or yes. And so as you can see, that would be kind of an impossible task to be able to test those. So even testing most of the permutation is not possible. It is also difficult to test the end conditions because a lot of the times we don't know what those end conditions are. Adaptation is always required to do any kind of testing. So now we're going to talk about testing at JPL, and these are all the different kinds that we have. We have a tenet that says, test as you fly as you test, which means that you can't test something on the ground differently than you would fly it. So we have hardware testing, flight software testing, something that's called assembly launch test operations, which I'll define later. And then we have the ground software, and I'm in the ground software. We have project testing. We have something called operations testing. So the teams that actually build the commands that go to the spacecraft have dress rehearsals, and those are called operations readiness tests, or ORTs. And then you have downlink software testing and uplink software testing. I do uplink software testing. So now this is just a little diagram of how they break their testing up. So for hardware and flight software, you have the hardware. It does subassembly testing, so you might be testing a couple of electronic boards, then you're assembling those electronic boards into some element, and then finally you develop a component. And so for flight software, you have unit testing, you have what they call subsystem testing, and the subsystems are things like the attitude control, which determines how fast the spacecraft's going in what direction. You have the command and data handling system, which is the computer on board. You have power, thermal, communication. Those are all subsystems. So each subsystem does its own set of tests. And then you have system tests where they work together, and then that combined, the hardware and the flight software combine to do ATLO testing. So now I'm going to talk about ATLO testing. So assembly, test, launch operations. The hardware is tested at the unit and component level. Now, for curiosity, there's actually 3 curiosities. There are 2 that are absolutely identical. One of them went to Mars. One of them stayed here because we don't have a mechanic on Mars that we can fix it. So we have to be able to duplicate anything that's going on there. And then we have, and that one is a clone of the one that's on Mars. Then we also have a third one, and that third one has the same mass as the one on Mars, because Mars doesn't have the kind of gravity that we have, so that one has, some of the elements are substitutes. They're not the real thing. So the flight software is tested with JPL test frameworks, VxWorks, and simulators that we built. Both are tested again in assembly, test, launch operations. And so now I'm going to show you a couple of videos. So the first one is that when Curiosity was traveling to Mars, it was put into the cruise portion, and so its legs, its wheels were up against its body. So one of the things that had to happen for it to be able to land on Mars is that the wheels had to be able to come down. And so in this video, this is the test where they tested that the wheels would actually come down. And I can play it if I can find my cursor.
Hi, I'm Savannah McCoy, and I'm the rover verification and validation lead. My job is to run system-level tests on the rover structure to ensure it's capable of the requirements we have for Mars. Basically, for the Mars program, we build 2 rovers in parallel. One's the flight rover, and one's the test rover, or DTM. The main difference between the flight rover and the DTM rover is that the flight rover actually goes to Mars. Just recently, we ran a major test called the Sky Crane Full Motion Drop Test. This test is to check out the EDL sequence, or entry, descent, and landing sequence, for Curiosity. For the first time, we're going to be touching down on Mars with just the rover's wheels. So this is the sequence leading up to that touchdown on Mars. Because this test is so important to the project, almost all of the team wanted to gather and watch the test. We actually projected it into multiple conference rooms around the lab so that everyone could have access to this very large milestone for our project.
Test is commencing in 5, 4, 3, 2, 1, fire.
The reason we do all this testing is to prove that what we think is going to happen actually will happen when Curiosity gets to Mars, and that we really understand the dynamics of these vehicles. During this test, everything behaved as expected. We were able to collect all of the data and instrumentation that we were hoping for, so overall, definitely a huge success. I'm Savannah McCoy, and this has been your Building Curiosity Update.
So the next test is going to show you more of the rover put together. And this one, basically the suspension on the rover is built so that that each wheel can operate independently and it can go over rocks. And that's called a rocker bogie system. And so this test has to do with testing that and testing the wheels.
My name is Sean Haggart. I'm a mobility engineer on the Mars Science Laboratory. So as you can see down there, we just recently completed testing the wheels and suspension system on the Flight rover. Now the mobility system might look familiar. It's a classic rocker bogie suspension system that we've used for the last 2 generations of Mars rovers. And it does a lot of things that actually the mobility system hasn't done in the past. So for this mission, the mobility system not only drives the rover around, it's also the landing gear. The wheels are actually the first thing that make contact with the surface of Mars. Now, just about everything you see on the mobility system looks black, but that doesn't mean it's all the same material. The tubes, the suspension arms coming down to the wheels, those are all titanium. The tires themselves, those are aluminum. The shell on those tires is actually a piece of machined aluminum that's about 30 thousandths of an inch thick. That's about the thickness of 7 pieces of paper. And when they're that thin, it makes them actually soft. And so they behave in much the way that a rubber tire would behave and give you that springy load for landing, for driving over rocks. This test was sort of an obstacle course for the rover because we have to drive over obstacles of certain heights. Those correspond to rocks of certain heights that we expect to see on the surface of Mars. And so those ramps were mimicking those rocks to make sure that we can actually drive over them and get to the science. Now you notice that it's 6-wheel drive and all 4 corner wheels steer. Now those wheels can steer plus or minus 90 degrees. And what that allows you to do is actually position the wheels, kind of toe in, and turn the rover in place. And that makes it a very maneuverable platform to position itself for science. Now what you saw in that test was actually top speed of the rover, about 4 centimeters per second. Or to put it another way, it takes about 40 minutes to go the length of a football field. We want to go slow, because when you're 50 million miles away from the nearest service station, it's okay to go a little slow and be a little careful. My name is Sean Haggart. This has been your Building Curiosity Update.
And I wanted to say something about the wheels. They have found that because they did make them so thin, that there are showing some wear. And so they are doing things to make sure that they really don't put the rover in situations where that's going to cause additional friction on them. So they were on their way to Mount Sharp, and they were going over a plain area, and it turned out that there was slippage on the wheels. So they have backed out of that area, and they're looking at going either to the north or south, I think is what they said. So the next one is, it talks about adding the arm. The arm on Curiosity is about this big around. It's not small. In addition, it has about half the instruments that are on Curiosity are on the arm.
Hi, I'm Ben Toma, the mechanical lead here for the assembly, test, and launch operations of Curiosity, the next Mars rover. So just recently we installed the robotic arm. That was a major milestone for the project, not only for the engineers that worked on this arm for years, designing, assembling it, and finally delivering it, but for the project as a whole. Having the arm on the rover is a huge accomplishment. Now we'll be able to begin the testing of that arm while it's on Curiosity. It's a very complicated, very tricky maneuver to actually put the arm on the rover. We use a crane from above because this arm is so heavy. We need to delicately bring it over and actually secure it to the front of the rover. We're going to go through a series of electrical and functional tests where the arm will actually be exercised. It'll move around. We'll start to learn how to use the arm with Curiosity. The arm is really one of the fundamental parts of our ability to gather the science. At the end of the arm, there's several different instruments. There's a camera, there's a spectrometer, and there's a drill that will deliver samples up to the other instruments on the rover. So without the arm, we wouldn't be able to do a good portion of the science that we're actually going to Mars for. There's still a lot of activities that we have ahead of us, a lot of testing. While we're working on the rover down here in this facility, we have the cruise stage, which is the device that actually takes the entire spacecraft to Mars. That's currently going through a thermal vacuum test up in our 25-foot space simulator. This is a big morale boost. Over the last couple of months, we've finally seen some of the major pieces of hardware get put on this rover. Going back for the last couple of years, we focused a lot of our attention on the inside of the rover. All the electronics, the telecommunications, the thermal control system. Just in the last couple of months, as you've seen, we've installed the mobility system, the remote sensing mast, which sits up on top of the rover with its cameras, and now finally the arm. The rover finally is starting to look like it does in all these beautiful animations we've seen. So the team is very excited at these major accomplishments and our ability to move forward with testing. I'm Ben Toma, and this has been your Building Curiosity update.
And so the last one, I wanted you all to see what it's like in the Mars yard. And so what kind of testing they do. One of the things that you'll see is you'll see guys carrying these huge cables. Well, that's what's powering the rover. They're not using thermal radioactive generators to power the rover at that point. So. It's difficult to find my cursor.
Hi, this is Richard Rainin, and this is your Building Curiosity update. I'm in the middle of the Mars yard at the Jet Propulsion Lab, where we're testing out an engineering model of the Mars Science Laboratory rover, more commonly known as Curiosity. The Mars yard was created to try to simulate the types of different terrains that we might encounter on the surface of Mars. We have everything on this Mars yard from rocks that are the size of about 25 to 30 inches in height to varying slopes, and the slopes vary from about 5 degrees all the way up to about 20 degrees, which is the driving capability of this particular vehicle. We've put flagstone on the surface to simulate bedrock. There's also loosely compacted soil. And in addition to that, we've over here created a sand pit with very non-cohesive sand, much like beach sand. If you recall, the MER rovers have had some difficulty when they've gotten into deep sand areas and actually have gotten stuck. So we're evaluating this rover and see how it behaves in the sand media. We're going to be driving up the rover on both flat sand as well as slope sand and evaluating how the vehicle behaves, how much slip, whether it gets itself stuck, things of that nature. We'll also be looking at the visual odometry markers that we have on the wheels. There are asymmetric patterns, actually holes inside the wheels of the rover, that will leave an imprint on the surface of Mars. It's going to be looking at these imprints and verifying that it has traversed the distance that it expects to traverse. If it looks like it's not traversing, even though the wheels are going, that is an indication to the vehicle that it is getting stuck, and it will stop and call back home. Testing with the vehicle has gone very well to date. The vehicle has matched our computer predictions in almost every way. From this point forward, it goes down into the test bed for avionics integration and further electrical checkouts. This is Richard Rainin, and this has been your Building Curiosity update.
So one of the things that you can see is that we do a lot of various different kinds of testing. This is the hardware and the flight software. The flight software is tested on the actual rover. So that testing is already done and done for my group. We don't have anything to do with that testing. We don't have to do that testing. So now we're going to talk about the ground software. And so in the ground software, we select frequently used elements to test. We do exploratory testing in building an automatic test. We actually are embedded with the software people, and we start building the tests as soon as they have anything that we can test with. We do not wait until it's test time. We're almost continually testing. And so we build the automatic components after we have done the exploratory testing. We do subsystem tests, which test the interfaces among all of those 19 elements, and then we personally evaluate those tests. Then typically it goes to project user acceptance testing. So that would mean that it would go to the people on MSL or Curiosity, and then they would test the same things that we tested, but more specifically for their mission. So the first thing that they do is they test their own adaptation to make sure it catches what they call flight rules, which are illegal things that the hardware simply can't do, so you don't want to be sending commands that are going to make the hardware try to do that. So they test that adaptation, then they do the user acceptance testing on the core software with their adaptation. For the uplink side, they also do the same thing for the downlink side to make sure that they get the information correct, and they do a system integration test, and then there are the operations readiness tests, and those use a spacecraft simulator. So when we test, there are certain things that we require. We have to have an adaptation. That adaptation can be a real adaptation for an existing spacecraft, or it can be a notional one where we've made up the commands, we've made up how the spacecraft behaves. Most of the time we don't have time to build fairly complicated generic spacecraft. The adaptation can simply be a configuration file. It might be more complex. For the simulators, it's always much more complex. We have to build models so that they can operate correctly. The adaptation can be input files, or it can be in code. It kind of depends on which application we're trying to test. And the adaptation must meet whatever format specifications are available. We have a set of automatic tests. We need the third-party software for any test tools that we use. And of course, we need some documentation on what's supposed to have been done. So this is what we test. We test functional capabilities, we test bugs, we test any kind of upgrades that we have. We test upgrades on operating systems or changes in test tools. We test adaptation capabilities. This means that if a spacecraft has some new capability and that mission's adaptation team, who are building the actual adaptation, need a different capability, then we have to put that into the software. And so then we test that they can actually use that capability. And we test the configuration files. Our tests are automatic. They tend to be success-oriented because I'll get more into that, but as you can see, the permutations are unbelievables, so that there's no way that we could test everything. And we do test some failure cases, but most of our tests tend to be success-oriented, because actually before the commands go to the spacecraft, there's a person who looks at them on the operations team as well. So these are our constraints. Due to the large number of permutations and combinations, we have to make choices as to which commands and which activities we're going to be testing. Spacecraft have launch windows. We can't miss the launch window. They had a delay on Curiosity. It cost 2 years because Mars is only in the right place for us to launch to get there. And so, you know, if you have a delay, it can be quite expensive. And then let me give you this little example. So I want to have the camera on a spacecraft take a picture. And so this picture, this is one activity, and it has 10 incoming parameters. So it has the number of rows I want. It has the number of columns I want for this mosaic picture. It has the overlap in the rows and the overlap in the columns. It has the filter that I want to use. It has the exposure I want to use. It has the XYZ location of the spacecraft. It has the spacecraft rate and the spacecraft acceleration. Now, if each one of those parameters only had 2 values, there would be 90 permutation possibilities and 180 combinations, and that's one activity. So for something like Cassini, which puts in a month-long sequence, they probably have 100 activities. And those are all different and varied, and so there's no way that we could test everything. So this is how we mitigate that particular risk. So the Class B components, which are the ones that we are the most worried about, they've been in existence for 20 years. Now, what that software was 20 years ago and what it is today are entirely 2 different animals. But it has morphed over time, and we've been able to test it frequently as it morphs over time. In addition, not only do we do testing, but the level above us does integration testing, and then in addition to that, the project does testing, usually at several different levels. So there's a lot of testing going on in spite of what we do or what we might fail. So far, we have not had any priority 1, which is mission catastrophic, or priority 2, which is mission critical bugs that we have to fix. All of our bugs are in category 3 and 4. And finally, it's tested again in operations. In those operations dress rehearsals, there are multiple ones of those, and it's tested in those particular ones. It's tested in the actual like I said, a dress rehearsal of how it's going to be used. And the last thing is there's only 2 of us testing, but between the 2 of us, we have a combined total of 70 years of experience at JPL. So we're a fairly experienced test team, even though there's only 2 of us. And all the developers support us. I mean, if we find a bug, the developers drop everything and say, "Oh, well, let me see, you know, show it to me. You know, thank you for finding it," because nobody wants to be that person who let a bug go through, that let a command go through, that harmed the spacecraft. You don't want to be the focus of a red team. So we have kind of a different mentality, I guess. So now we come to the final. Why I think it's 3 parts art and only 1 part science when one would think it would be mostly science. So basically the art is how do you pick the software functionality that you're going to test? What adaptation characteristics are you going to test? And what rules are you going to test? Typically, all hardware rules are tested. So that's the art part, is how do you pick these things? The science part is actually knowing enough about spacecraft and how they work and how the operations teams work to be able to make those choices and make good ones. So that's why I think it's 3 parts art and 1 part science. So that's my concluding slide. I did want to show you the difference in the 3 rovers that we have. The large one is Curiosity, and it's the size of a Mini Cooper. The middle one is Mars Exploration Rover Opportunity, and it's the size of a smart car. And that little guy on the end, that was our first one. That was Sojourner, and he's the size of a large Tonka truck. So I thought that for the final thing that you might like to see the animation again. That's if I can. That's the booster. And now we have the cruise phase. The cruise phase fell off. Heat shield came off. You can see Curiosity's tucked up underneath there, up there. Its little wheels are up. The rockets are firing to slow it down. That's a laser that's on the mast, and what it does is it clears away the surface area. So basically it got soil and it placed it inside the rover, and now it's baking it so that the rover can determine what kind of minerals that rock is made out of. Takes a long time. So that's why you have the clock. These little holes, there's only a certain number of them, and so they can only do that many samples. And that's it. Thank you very much for your attention.
Great. Thank you very much. Now it's time for open season. 100. Any others? 122, right? 116 to start, please. Was here? No. All right, 200. 216.
What was that?
Go ahead.
Oh, okay. So I think you touched on, you talked about a little bit of the...
Sorry.
Oh, yeah.
You have to signal a runner.
You mentioned, talked a little bit about like the integration testing that you do. Can you kind of go into a little more detail as far as like what testing boundaries you approach? Like as far as, I know you said you worked on the ground software, so do you go all the way through like the uplink and then all the way to the flight software, or do you only test to like the interface of the uplink and download link?
Okay, the ground software is typically tested together at some point. Right now, we test only the uplink side, my group. And so we go from creating a plan, and then, of what kind of activities people want to have on the spacecraft. And then once you create the plan, then they evolve that into commands, then they build the binary, then they build the packets, and then we send it on. And so that's the limit of what we do. Then as far as integrating that, that's typically up to the mission. So the mission will take our uplink software, they'll adapt it for their mission, because every mission has different commands. Every mission has everything different. So they'll adapt it, and then they'll get the downlink software, and the downlink software does the same thing. And they'll hook the two together, and the mission actually performs that integration test.
Okay.
Now, with flight software, the ground side typically is not involved in the flight software. Flight software goes through a different process and is hooked with the hardware.
So you have like a global team that kind of does, the really specifics, but then a separate team kind of does the integration piece of it?
Typically.
Okay.
Because it's mission specific.
Okay.
So we can't do all the mission specific stuff. And so you have to integrate it with all the mission specific information.
Thank you. Number 100.
Hi, Tom Staub from LiquidNet. I would imagine the flight software has, a couple levels. There's probably like the application that sits on top of the OS.
No, there is no OS. The flight software is the OS.
The flight software is the OS. So I would imagine there's some kind of bootstrap underneath that.
Yes.
Just the extremely low level.
Right.
So, God forbid a bug is found after deployment in the flight software, can the actual OS be re-uplinked?
Yeah.
And
we do it all
changed?
the time.
Okay.
Because the thing is, as the longer that a spacecraft is out there, the more difficulty it has with various different things. And so the flight software sometimes deals with that. And we've had, for Spirit, when it first got there, we had a huge flight software bug. And so they had to uplink new flight software to get around that bug. So the thing that happens is that all spacecraft have what they call a safe mode, and in that safe mode, they're generally not doing anything. They're just sitting there waiting for you to fix them. And so that's the way it works. And then we upload something. But they test the flight software on the Mars yard, on the clone. It doesn't go up without testing on the on the clone. Okay? Does that answer your question?
Did you ever get to
Press the button on the left.
It's still not working. Closer? Okay. Have you ever been able to watch one of the launches of one of the vehicles that you tested in person? And if so, how was that experience?
Well, let's see. That's kind of twofold. I have not been to Florida, which is where they are typically launched from, although Jason was launched from Guyana. I have not been there in person, but when MSL was launched and also when it landed, I got a special, note to come on lab at some ungodly hour of like 4 or 5 a.m. in the morning with my granddaughter, and we all sat in this big room and watched it go up. So, and it's not the same as watching it in person, but it's a lot closer than what you get to watch. And it's pretty cool. Yeah, if I got a chance to go to Florida, I would.
Next one is 116.
Okay, yeah. With the landing, do you actually how do you actually simulate the difference in gravity between Earth and Mars for the landing?
Well, that would be there's a special team called Entry, Descent, and Landing. When you were watching that one test where the rocket bogies came down, the young woman was standing with a couple of gentlemen, and they're the Entry, Descent, and Landing team. And they're the ones who figured this all out. They're the ones who came up with the idea that they could build the sky crane, because prior to that time we had put things into balloons. And so they came up with this design, and of course nobody thought it would work. And so they had to do a lot of testing to prove that it would work. But that's how they're the ones who have the knowledge to be able to do the differentiation. I'm not on the Entry, Descent, and Landing team.
Bernie, you were green, not yellow, correct? New idea? Okay, I'll catch you in a moment. 200?
Hi. Yeah, I just want to thank you for coming here and sharing, JPL information with us. It's kind of, sometimes we, I know for me, testing a lot of times with within web development or desktop, web applications, it's sort of breath of fresh air to kind of see, testing outside of that. My question is with regards to, I know you touched on a little bit of the combinations of different testings that you guys do with in the, I guess it was 10 to the 27th. What would be a way that, or what was the way that you went around about tackling all the the different patterns for specifically that situation? Because sometimes within web development or web testing, you do have many patterns that you have to test, and you don't want to exhaust all. I mean, you can't exhaust all those things, but you want to make sure that you touch on everything. So, what was some of the ways that you went about?
Well, the first. Well, there's a couple of things. One is the person that I work with has done adaptation for MSL as well as many other different projects. So he was very aware of the kinds of activities that they were going to do on the spacecraft. So that knowledge enabled him, along with me, to pick out the things that they most commonly would do. And so that's what we test, is the things that, you know, the middle of the road, you know, what are you going to do most of the time, and especially if it's something that could cause a hardware failure. That we have things called flight rules and mission rules. Flight rules are things that the hardware can't do or is definitely not supposed to do. And so we build models to be able to trap that. So we do that testing, but then MSL, they went in and they do their adaptation and they test as well. If it's a particularly tricky activity that's going to be on board, they test it on the hardware or they test it on a simulator. You know, if it's more common and something that's done regularly, then we've already tested it. And the MSL project has tested it as well. And a lot of times they'll come to us and they'll say, we have a huge bug and we have to drop everything. Everything's gone. If it impacts them a lot, everything's dropped and we fix it. So.
Okay.
I don't know if that helps.
Good. So we have plenty of time at this point. I have 148, 220, 215, I mean, twice, and 203. Did I miss someone? Okay, Bernie, you want to go? 115? 215? Please stand.
Hi. I'd like to say that this was absolutely fascinating, and like you mentioned that each spacecraft is one of a kind, I would venture to guess that this type of testing that you're doing is also one of a kind. And so I was wondering if you have any thoughts about what lessons that you could share from this one-of-a-kind testing experience that you have that might relate to other domains, such as, you know, business domains in computing.
Well, there are a couple of things. One is, before I came to this task, they basically would be like everybody else, where you run really fast. You know, people would be developing up till the last minute, and then all of a sudden the test people had to come up with some way of testing what they had developed. And so now we don't do that. What we do is we do Scrum like everybody else, and with each bug, new feature, or new capability, each one of those things has to have what we call a test subtask to go with it, at least one. It depends on how big this element is. But this test subtask is not really to run the test. The test subtask is to do the exploratory testing and to come up with a way of testing it, and if it's possible, to automate that test. So that's something that anybody could do. That way you're not backed up, clear to the, you know, you've got 2 days to do testing that would take you a month to do. And so I would recommend that, you know, that you actually do that kind of thing, that you start the testing a lot earlier. We test all the time. We test every day. There isn't a day that goes by that we're not testing something. And we work very closely with the developers, and even though we're not exactly like the keynote speaker after lunch, we're embedded with the developers. We talk to them every day. Our sprints are with them. Our stand-ups are with them. I'm the Scrum Master. So that even though we're separate, we're not actually doing the same tasks that they're doing like she was talking about. We're still very embedded with them. And I think that that's a model that testers should be working on. You should be involved in learning what the developers are doing, working with the developers, being involved in the sprints, being involved in the stand-ups. Does that help?
Good. We have a tweet question, so it's from Chris. Since JPL is government funded, what type of test standards in process and documentation do you employ, if any? And is any government audit expected?
Yes, to all the above.
Can you elaborate?
You want me to elaborate? Okay, we have to document everything we do. We have gates that we go through. We have test readiness reviews that have to be done before we start the testing. Now, we have been testing all along, and so our official testing doesn't begin until after the TRR. And then we have a delivery review, and we have documents that are due for each one of those things. And yes, we are audited almost every week by some government agency for some purpose. We have monthly manager reports where people give their current status. And then there are programs, like we work for a program that's called the Multi-Mission Ground Services and Systems. And that group reports to NASA. So we have everything. Now, some of our documentation now is in Confluence. We use JIRA to track our issues. We have pointers and links to things so that documents aren't actually the same as what they used to be. So we have automated some of that.
Great.
Does that help?
Yes, I think it does. 148 is what I wrote down.
Good afternoon, Barbara. Enjoyed the presentation.
Can you speak up?
Okay, a little closer. There we go.
Yeah, that's good.
Okay. Is the bulk of the testing done against a simulator or the actual clone spacecraft?
It depends. First of all, the flight code will be done first with their test framework, and then it will be tested using VxWorks. It might be tested against the test bed for MSL, but ultimately the flight code before it's uplinked will be tested on the clone. So it will go through all of that testing. For the ground software, we basically don't, our code is the simulator. So we don't test against the simulator, and we don't test against the spacecraft, the clone. Typically, our work is done on the ground, and there are people who are on operations teams who put the commands together and run that software. And they're the sort of the last resort. Now, if it's a tricky thing, if it's something that's unusual, they will test it on the clone. They will test everything. You know, it depends on what it is. If it's an orbit insertion, you bet it's going to be tested on the clone. EDL is a non-interruptible sequence of events, and it was tested.
Very good. We got 12 minutes left. We have 3 people on the stack. We have a tweet question. Is real-time data validation used when getting sensor data from rovers?
Is what?
Real-time data validation.
I don't know what that means. We don't get real-time data from anywhere except maybe the moon. The one-way light time from Mars is around somewhere between 8 and 20 minutes. For Cassini, it's an hour and a half. So real time is relative. So I'm not sure how to answer that question. Okay. I'm also not sure what it means.
Okay, clarify. If they could clarify, that would help. Bernie.
My second question was answered. My second question was answered.
You're off? Okay. You're up.
Okay, so in the industry that I'm in, we work on monitoring systems that are, in charge of protecting large machines and actually preventing human lives lost if they explode. So and I assume, like, with the expense of some of these spacecrafts that are being built, that you all have certain requirements to test to as well. So what sort of, like, fault injection type testing that you all do? Like, for example, one of the scenarios that they always give us is like cosmic bit shifting in some of our software that's running on board our hardware. So do you, like, with the extreme, environment that Mars is in, like, what type of testing do you all do around that?
Well, this is something that's done more in ATLO. And of course, that's not my area. So I will try to answer this as best I can. They have something called where they can fix the bits, and they test that. So you have the ability to fix some bits. You also have the ability to not use some bits. We had a problem on Curiosity where it hit a critical area for storage of files, and that caused a problem. We went into safe, and so they basically excluded that area of memory. We can't protect against everything. I mean, Cassini was hit 1 million times by the particles in the rings. So we use space-hardened components and have the ability to either exclude bits or do that cleaning of the bits. I can't remember what it's called. You probably know. Yeah.
You good? At this point, the queue appears empty. Is there more questions? We have 10 minutes. Okay. 084. Oh, I'm sorry. You first, and then we'll give you priority. What was your number?
Hi. I'm surprised to hear that exploratory testing and Agile is used at JPL. It's awesome. I'm just curious to hear, like, who or what brought that about, and are there any, like, software development or testing methodologies that you wish came back, went away? Because I think you mentioned, between you and your colleague, you had like 70 years of experience in this field, which is a lot more than I think most of us in this room. So there you go.
Well, I don't ever want to see waterfall again. So, Agile, using Scrum and doing things the way we're doing them, the system engineer for the core software and I collaborated and brought that in. Adding the test subtask was my idea because I don't like getting to the end of things and having to rush. It's especially not something that I think that JPL ought to be doing. And so that one was my idea. We typically at JPL is one of the few places where you can come up with an idea, and if that idea is a good one and you can convince other people that that idea is a good one, then you can do it. So that it's one of the more open places for coming up with new ideas. I mean, the Sky Crane was totally out of nowhere.
So same thread.
I just had a quick question. Like, what is the length of your
stand up and talk?
What is the length of your sprint cycles that you are doing?
We're doing a month.
Okay.
We started out doing 2 weeks. The difficulty, we had a number of difficulties in fitting into Scrum. Fortunately, Scrum is flexible enough, and we went to the Scrum Master class, and that particular instructor was very helpful in helping us to come up with things, because we have to schedule things in such a way that a mission can come in and say, I need that. And we drop everything. And so one of the tenets of Scrum is that you don't interrupt your sprint. And so we schedule everybody at halftime. Another thing that we've done is during testing sprints, we still sprint. Some people don't sprint at all. We still sprint so that we know where everybody is and what they're doing. But we only meet Mondays and Wednesdays. So we shorten how many times a week. And right now, we have people who are working half-time on one project and half-time on this project. And so we're keeping the Monday, Wednesday.
We still have more than 5 minutes, so go ahead.
Hi. You mentioned you have several different copies of the same hardware, and you go, when you test something, you go through the simulator and then the hardware, and especially if it's something tricky. And I'm very curious, have you ever actually broken the hardware of something that you've sent away? And when you've tested, can we do this? And when you tested it, it actually breaks, so you catch a bug?
Well, let's see. I can tell you about Mars Polar Lander. Mars Polar Lander was supposed to land at one of the poles of Mars, and the software that we were using that was written by a subcontractor was not adequately checked by us, and they were using foot-pounds, and they were supposed to be using newtons. And supposedly there was software that was supposed to convert them, but that software never got written. And so the error ellipse telling us how close we were to Mars was incorrect, and Mars Polar Lander became one with Mars. So, so yes, we have had failures, and we have red teams, and we take everything very seriously. We tend to question absolutely everything. Some people are somewhat offended by that because we're not always tactful. And so we have had failures. But for the most part, like the Mars Exploration Rover, currently the Opportunity that's on Mars, it's traveling in reverse because it has a bum front wheel, and the arm can't be stowed. If it's stowed, it won't come out again, so it's traveling, so it's kind of limping. But it's still operating, and it was only supposed to operate for 3 months, and it's been operating for 10 years. And so that I can understand it's a little decrepit in its old age. We have even, that's what I mean with, as the spacecraft gets older, it has kind of tricky things. Cassini has some reaction wheel problems where they have to be very specific about how they turn the spacecraft. And it's on an extended mission. I think it's its third extension. So these spacecraft do pretty well.
Nice job. At this point, the queue is closed, and we only have 1 minute left, so I think we should...
Oh, he has...
Oh, you had another question? Go.
Yeah, that was also interesting, but what I actually meant was, have you caught something that could have broken the away unit, and you've caught it in the lab when you tested it?
Oh, I'm sure. We catch things all
by
the
breaking
time.
it.
What?
Something that would have broken it.
We always catch things. There's always something that would have broken it. So I know that they have caught things. I mean, just for one example, the actuators on Mars Curiosity were not performing correctly. And so that's why we scrubbed the mission for 2 years. And so that was caught. So they always catch things. There's always stuff, but there's always something that usually happens there as well. There are things that we can't catch everything.
Of course.
But we try to correct it.
Okay.
Of course. Thank you.
Okay, one last question, 041.
Cheers. It's a very quick one. Just, is there a difference, do you know, between the testing that you did on this, which is, just a robot, and the manned space flights?
Oh, yes. But we don't do manned space flights. But I have worked at JSC, and they are unbelievably rigid. And they test everything over and over and over again. And they have definite written down procedures that they have to follow under every single situation. The Apollo 13 movie, if you look at the command room, that's what it looks like. They have it there at JSC. They have mock-ups of all of ISS, the International Space Station. They have a mock-up of the space shuttle. They have a mock-up of Soyuz. And everybody exercises in all of these things. They have a pool, a swimming pool that's as big as this room, and they have mock-ups of the International Space Station underneath it. They have divers that go with the astronauts when they're practicing there. So, I mean, when you're dealing with human-rated, you practice everything. Everything is tested forever. So.